At 8,849 meters, Mount Everest is the highest point on Earth. A slow-motion collision between the Indian and Eurasian tectonic plates began over 50 million years ago, buckling the crust upward to form the Himalayas. Under normal geological conditions, major fault lines create a relatively even distribution of mountain heights. Because the underlying tectonic forces are consistent across the region, neighboring peaks generally reach similar elevations. This graph maps the height progression of the highest Himalayan peaks. Makalu, Kangchenjunga, and Lhotse follow a linear path, differing by only 120 meters. But Everest breaks the curve, sitting 250 meters above its closest neighbor, a vertical leap standard geology cannot explain. Everest is a geological outlier. The data suggests that while colliding plates laid the foundation, a secondary, hidden force is pushing the summit higher than everything else around it. GPS instruments placed directly on the mountain show that this vertical movement is happening in real time. The peak is currently rising by about 2 millimeters every year. That is double the long-term tectonic uplift rate observed across the broader mountain range. Tectonic plates provide the foundation, but a localized force is giving Everest a specific, measurable boost. This is an aerial view of the Arun River basin, located about 75 kilometers east of Mount Everest. The Arun has a strange topography. It begins in Tibet, flowing quietly eastward across a flat, high-altitude valley, but then it makes an abrupt 90-degree turn to the south, dropping steeply to carve a gorge 7 kilometers deep. Roughly 89,000 years ago, a process called drainage piracy fundamentally reorganized this system. Through aggressive erosion, the Arun River breached the drainage divide and captured the water flow of the neighboring Kosi River network. This merger multiplied the Arun's water volume, giving it the hydraulic power to carve through the landscape, washing away billions of tons of sediment. That missing mass is the culprit. Removing billions of tons of rock and soil from the region near Everest's base triggered a mechanical response in the Earth's crust. This response is a geological process called isostatic rebound. The Earth's continental crust floats on the denser, semi-liquid mantle, much like a ship on water. Remove heavy cargo, and the vessel sits higher. As the Arun River carved out rock, the lightened crust flexed upward, pushed from below. Because the crust is elastic, this upward flexure extends for hundreds of kilometers, thrusting the mountain peaks higher into the sky. This is a geological diagram mapping the results of that upward flexure. According to researchers, this river capture has pushed Mount Everest 15 to 50 meters higher than it would have been without the river's erosion. This creates a feedback loop called fluvial tectonic coupling. The river's erosion removes weight from the crust, and the mantle responds by pushing the surrounding landscape upward. While the river wears down the valley floor, the peaks at the top experience almost no erosion. This means nearly 100% of that upward flexure translates into the mountain getting taller. Everest is a responsive feature of a dynamic planet. It is still reaching higher today because a river 75 kilometers away is digging a hole.